I'm going to ease you into it. I'm not going to call it calculus. I'm going to call it trig. I'm going to show you a reasonable way of doing it. Okay, so I got speed, which has two components in this case. You got the velocity, which has two components. You got a y component and an x component. And the way to do it is you make a rectangle, and then you draw a vector connecting these two edges. Then notice that the bottom one, I'm going to turn that into a triangle, right angle triangle. Yeah. And then I'm going to do some weird. Okay, so velocity vector is along this direction. It's an arrow, guys. You can move it up and down as long as you don't change its magnitude and direction. This is free to move anywhere you want to put it. So this is the same as this. So I just move it down and I create myself a triangle, right angle triangle. So this is your velocity vector along the x direction. This is your velocity vector along the x direction. This is along the y direction. This is along the x direction. And now this becomes the hypotenuse of this triangle. Hypotenuse of this triangle is your net speed. This is your total speed that you're looking at. All right, so this is going to represent your total speed. All right, so if this is a triangle, how do you figure out hypotenuse? Pythagorean theorem. All right, so the square of the base times the square of the height is going to give you the square of the hypotenuse. So in essence, that's what we did. Is this what happens? This phi is the final speed, the resultant speed, total speed. And then next thing you have to do is just numbers. All right, so in terms of meters, this is what you get, but you're interested in the speed in terms of the number units that you're interested in. That's 86 miles per hour. Okay, so the impact that you saw was a guy hitting the water at 86 miles per hour. Okay, so another thing I'm interested in, angle of impact at this point. Okay, so I can construct, that's the speed. So with the angle now, I get a velocity. So what is angle of impact? That looked very shallow the way he hit the water. So the way to figure out the angle of impact is, number one, the angles will always be measured with respect to the x-axis. So it's going to be right there. And this angle that you're looking at is the same as this angle inside your triangle. Got it? All right, so you know the y component of the speed. You also know the x component of the speed. You also know your total speed along this direction. So which means that you can potentially use the sine of the angle, the cosine of the angle, or the tangent of the angle. Now, traditionally, we like using the tangent of the angle because normally you would figure out the x and the y components of the speed first, and then from that, you can easily figure out the angle of impact. So traditionally, that's what we use, so that's what I'm going to use. So by taking the inverse of tangent of both sides to isolate the angle. All right, so into the formula, you got the numbers with metric units. And that's going to give you a shallow angle, which is about 21 degrees. All right, so this is the entire projectile motion, high school style, one step at a time. All right, that's it. Okay. Next thing I'm going to do is I'm going to now, I will tie the projectile motion to impact, and then we'll do an impact analysis. All right, so let's analyze the impact. There will be some assumptions that's going to go into this, and I'm going to clarify every single assumption as I'm making these assumptions, because the accuracy of the results will depend on the accuracy of the assumption. So I'll just justify the assumptions as I'm making it. Number one, I'm going to end the motion right at this point. There's a secondary impact. Notice that the person bounced up. Mathematically, it's kind of complicated, but it's doable. But just too much work. I don't want to complicate it. This is just a lecture. So I'm trying to get a really good estimate of what happened to this guy. So I'm just going to go hit water at 86 miles per hour. And that's 39 meters per second, roughly, 40 meters per second. I'll bring him to a stop within 1/10 of a second. Okay, 1/10 of a second is the time it takes for the pain to register. So I want him to know that he just hit something that felt like concrete. All right, and then I'll bring him to a complete stop at that point. So it'll just come to a complete stop. So final speed in projectile motion is going to become initial speed and impact. This is going to be his impact time. Roughly, I'm giving him 1/10 of a second because the water is going to give. Then it'll come to a complete stop. So there's no bounce or whatever. So we're ignoring the reality. So what is the acceleration in terms of g's? So what you know that number one, something is going to happen to the body. Bones will crumple or crash or break or whatever. So body's going to go through a jerking motion. So which means that I want to get a good estimate in terms of what the average acceleration is. Okay, notice that I modified the notation. So I said this is the impact, estimated impact time, estimated impact time. So these are just estimates. I'm trying to get an idea. So I'll also make the assumption that it comes to a complete stop. Boom. Okay, so there's a negative, which means that it's slowing down. All right, so we do the numbers. Okay, and then move the decimal to the left. It's going to give you about 38 Gs, about 40 Gs for a fraction of a second, 1/10 of a second. Okay, now we have to draw a conclusion based on that. I'm thinking give and take 40 Gs for 1/10 of a second. That's what he's going to experience. So the question is that survivable? Now you have to draw, you have to make it, you have to come up with a conclusion. Every single task is going to ask for a conclusion. All right, so is this survivable? Can you survive 40 Gs for a fraction of a second? So what do we know, guys? We know that you should be able to survive under extreme constraints, up to 140 Gs. So 40 Gs should be survivable. For 1/10 of a second, you should be able to survive that. In fact, John Stapp survived. He didn't survive this number. Yeah, so 40 Gs is survivable. except there's a problem. This range, anything over 25 G's, potentially you're breaking bones. All right, so of course you can break your neck and die from it, but more than likely, barring breaking your neck, you should be able to survive this. So the conclusion is, it should be survivable with broken bones. That's what it is. All right, so now this conclusion was sensitive to the assumptions that I made. So let's go back. Now that we got a rough idea of what he was experiencing, let's try to come up with a little bit better conclusion out of this. Okay, so move forward.
Now, he's off the fuselage. The aircraft approaches the drop zone.
All right, so in my assumption, he came to a stop at this point. In reality, he did not. What happened was he bounced at that point.
Television cameras, aircraft approaches the drop zone.
Instead of coming to a stop, he just bounces. His impact time is actually shorter than a tenth of a second at this point. Okay, so whatever happened, he didn't feel it at this point. The pain is not going to register. On top of that, not only did he not come to a stop, he ended up changing direction. So this acceleration is going to be more than 40 Gs. Potentially it's 50, possibly 60 Gs. This is large enough to shatter bones. I expect him to be able to survive that, obviously, unless he broke his neck, which he did. Quite a few broken bones.
Slammed across the surface of the water.
And that's exactly what happened to him. He ended up breaking his ribs. He passed out immediately. He has no recollection of what
And now, he's not moving.
And he survived.
Another look at the ill-fated stunt reveals that the plane was traveling much too fast, by smashing into concrete. The rescue team quickly moves in and soon has Jean-Louis safely out of the water.
Okay, so we'll get to do the same problem. This time you will apply it to a different case.
Again,
I guess this is going to be your homework. I'm not going to collect it. And you will get a weird version of this problem on the test.
according to plan, as they leapt off the bridge while
My recommendation is know how to do this as many ways as you can.
tethered to the cable.
And you won't be able to solve it one step at a time. There's a good reason for it.
Stand up. For three, Thomas? Great. 1, 2, 3, go.
But as the team was about to reach the end of their first arc, the cable snapped, and 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't see just disconnect, my arm goes out, and here we come to the water. Pow! Oh, a ton of bricks. So look at the splash, like 40 feet. Big action though.
Again,
Okay, I'm on the outside, does the front flip. Here we come,
Okay, so by the time I'm done with you guys,
going into full
you'll be seeing it at least 10 more times.
velocity right here.
There's a lot of physics packed into this clip.
Probably reached about 78 miles an hour, right about here, 78 miles an hour.
Imagine there's roughly about 80
You'll see the harness
at the time the cable snaps.
disconnect from the cable right there. Didn't see
Now it's sideways projectile motion.
just disconnect, my arm
Initial horizontal speed is 80.
goes out,
As these guys are falling vertically,
and here we come to the water.
a distance of 70 feet. Okay, so it's exactly identical to the previous example problem. Okay, so they're moving at the same speed at 80 miles per hour as they're falling on the horizontal, vertical direction at 70 feet, a distance of 70 feet. Okay, so if the impact time was 10th of a second. The question is survivable? Is that survivable? And what's the damage? All right, so that's what you will get to investigate. So this is from the handout, it's problem number 3. So that's your homework. I'm going to move on to problem number 4. So far, we're doing procedural problems. I got news for you. We haven't done a real physics problem as yet. Okay, so this is your first real physics problem. So this is going to illustrate how problems will get solved at this level. Okay, so involves this problem number 4. So you're throwing a ball horizontally from the roof of a building. So the building is 70 feet tall, and that is going to land 20 feet from the base of this building. So the only thing I want to know is the initial speed of the ball. That's it. Wow. All right, so I'll draw things out. So it's being projected from the roof. All right, so this with unknown speed. All right, so the from a height of 70 feet, and it's going to land 20 feet from the base of the building. Assuming that the gravity is the only force acting on it, so that's the effect of gravity. So the question is, what is the initial speed? Okay, so before doing anything else, guys, just make sure the units are the proper units. Okay, so just don't jump into anything, or else you're going to feel like you're burning in the pit of hell. Okay, this thing gets really complicated, numbers not expressed correctly. Okay. All right, so how do you solve a problem like this? Okay, it's no longer a procedural problem. This is like a real life problem. You don't have the luxury of, oh, I'm going to look at my symbols and then pick the best formula possible. It's not going to work. I wouldn't give you anything that simple. You guys are engineering majors or hardcore science majors, including physics. Okay, so how do we do a problem like this? All right, the way I would approach these problems, every single person may have a different way, but you still have to show work. My approach usually is just whatever it is that I need to solve, I'll just go after it directly. Okay, so I'm just going to go after this. So I'm going to look for a formula that has the initial speed in it. Mean initial speed along the x direction, formula number 4 and 5 will have the initial speed along the x direction. So that's what I'm going after. 5 is useless. It says the initial and the final speeds are the same. 4 is the only one that I can use. So I'm just going to grab that blindly, and I'm just going to wrestle with it. All right, so I grab fourth equation, and I'm going to wrestle with it. Okay. The way we will play this game, you do your algebra. I'm not going to allow you to I'm not going to allow anyone under any circumstances to use numbers. Okay, understand, this is the game you play. You can solve the problem any way you want, provided that it's multiple choice. I don't care about that. All right, when you do show work problems, you do not, under any circumstances, use numbers. You can use a calculator to do the conversions, but 99% of your work is going to be done symbolically. I don't want to see any numbers. If you're thinking you got the freedom to do so, absolutely, provided that you understand that you will lose a lot of points every time you deviate from what I'm asking for. All right, so now we got problems. The problem is you got two unknowns. You don't know the initial speeds, you don't know the time. So the next thing you need to do is you need to find an expression that's going to give you time. Fourth formula has time in it. Obviously, that's the one you're using, so you cannot use it again. So you have to look at the first one and the second one to see if you can use the second one. Well, for you to be able to use the second one, you have to make sure that it says only one unknown. You don't know what the final speed is on the y direction. Notice that you don't have a symbol for it, so you cannot use that. Get the first one, check to see if you can use that one. You got an expression for g, obviously. You also have an expression for the letter y. Yeah, this is good, so pick that one. All right, so you say, okay, so I can get my time from there. So grab the first formula. All right, solve for time, and then substitute back into this formula. That's what I'm going to do. Okay, so we will do a lot of back substitutions. All right, so I want to get my unknown on the left-hand side, so get rid of the 2's and g's. Boom, boom, boom. All right, so get rid of the square by taking the square root. Okay, so that's the final expression that gets substituted into that one. All right, all right. Before I isolate the initial speed on the x direction, I check to see if I'm done. Do I have a number for x? Do I have a number for the letter y? Do I have a number for g? I check, so I got a number for the letter y. I get a number for g, so I'm good with that. Do I have a number for x? I do. So it's solve for the initial speed on the x direction. Right, so I'm not going to show work at this point because evidently I was running out of time. So I end up dividing both sides by the expression of the radical, and then I inverted the radical, so I was able to isolate that one on the left-hand side. And into this formula, you put numbers. Okay, so I stopped working. Okay, I think I ran out of time at that point, so I have to go back and complete it. But